This is the second video in a series of 3 videos associated with using the PV and or TV vapor dome diagrams to help you solve engineering problems in your thermodynamics class. So let's go ahead and get started. So as I say, part 2, and all we're going to cover here is 3 examples of 3 example problems. It's going to be 3 different processes, and the interest is fully solving the problem, but also showing how do we show those processes on the PV and TV diagrams, and how do we use those diagrams to our advantage in solving the problem. Okay, so it's hard to know when you're watching this video. So I do need to let you know, here's what you're going to need, the skills that you're going to need for full understanding of the solutions that are covered in this video. The first thing is you need to have a basic understanding of phase change substances and understanding phases. In other words, is it a compressed liquid? Is it a saturated liquid? Is it a saturated two-phase mixture of vapor and liquid? Is it a saturated vapor? Is the phase a superheated vapor? So you need to have an understanding of that. You also need to understand how to find needed thermodynamic properties in the back of the book, things like specific volume, internal energy. You need to have a little experience in doing that. I'm hoping that this may give you a little refresher course in evaluating those thermodynamic properties, though. You need to understand how to determine the work out, let's say in kilojoules or foot-pounds or BTUs, for a closed system undergoing a quasi-equilibrium process. This should come something should pop into your head when you see closed system, quasi-equilibrium process. Something should pop into your head on how to determine the work out of the closed system. And finally, you need to have an understanding of how to use the first law of thermodynamics for a closed system. And one thing I've been telling folks is whenever in a word problem you see the word find the heat transfer, or maybe heat transfer given, or things like that, that's nearly always a clue that you're going to be writing down the first law of thermodynamics for a closed system to solve that problem. Okay, so let's get started on example 1 of 3, and I'll just sort of read this problem aloud while you're scanning it as well. Tap water with a temperature of 19 degrees C in the amount of 3 kilograms is placed into a vertical piston and cylinder. The piston has a mass of 20 kilograms, a cross-sectional area of 0.01 square meters. The pressure of the surroundings is 101 kPa, atmospheric pressure. The water inside the piston and cylinder is heated until the contents becomes a superheated vapor with a temperature of 120 degrees C. And so you're asked to determine the work done during the process and the amount of heat transfer during the process. And what I want to try to illustrate is how can you use the pressure volume diagram to your advantage to get this problem solved. Okay, so let's reread the problem and look for clues. So you see the word tap water. Well, that should immediately disclose that you've got H2O, it's water, and it's a phase change substance. And another thing about tap water is common sense 101. It says temperature of 19 degrees C coming out of the tap. Atmospheric pressure. That's below the boiling point, isn't it? The boiling point of water at atmospheric pressure is around 100 degrees C. So that tells you that the initial state phase is compressed liquid. So that's a clue, okay? Closed system, vertical piston and cylinder, that's a giveaway there. Another thing that I underlined here is this was a little bit of a gift in the problem statement. It says heated until the contents become a superheated vapor. So that discloses the phase of state 2, doesn't it? Okay. And now it says determining the work done. Hopefully that will, let's see, the work done. For a closed system in a quasi-equilibrium process, it should pop in your mind the work is the integral of PdV or M integral PD little v. Those are identical from 1 to 2. Work done. I hope that, boom, you say, I've got that. I think I can get right to that. And then the amount of heat transfer during the process, keyword heat transfer, that's a clue that you're going to be using the first law of thermodynamics. All right, so let's start solving. Okay, if hopefully you've had time to think about problem. Where am I going to start? Well, let's start with a sketch. Here's our piston and cylinder. I've written down closed system. I'm showing heat in, work out. I'm showing that I've got H2O contained in a piston and cylinder. I'm showing kind of depicting state 1 and state 2. And so then I start thinking, where do I start? Where do I start? And for this particular problem, I think I'm going to start with a free body diagram because I need to determine the pressure inside this piston cylinder with the H2O. And another thing I will want to learn from my free body diagram is that once I determine that pressure, I'm satisfied that that pressure is going to stay constant throughout the process, because when I look at the free body diagram, there are two downward forces, but they're both constant, aren't they? The weight of the piston is mg, and the force of the atmosphere pushing down on the piston is P atmospheric times A. So those are all constants. And so immediately I would, in writing my solution, I've got P, pressure equals P1 equals P2. And I've gone through the math that you can see with your eyes. I don't need to read it to you. And numerically, with these input values, I get the pressure P1 equals P2 equals 120.6 kPa. So that's a great place to start. If that's all you can do in solving this problem, at least that gives you some partial credit, right? But let's move along. Let's get this thing fully banged out. The next thing I'm going to do is draw the process on my pressure volume diagram with what I've learned from reading the problem. State 1 is a compressed liquid. It's tap water. So at least I know I'm going to put a dot. Here's my initial state over here to the left of the dome, compressed liquid. I'm satisfied that it's going to be a constant pressure process. So I'm going to draw a horizontal line. And probably by process of elimination, I know it's given that I'm going to the superheated vapor phase. So I'm going left to right across horizontal line, constant pressure. And I put on my PV diagram that P1 equals P2 equals 120.6 kPa. Okay, that's another partial credit. Okay, I've drawn a PV diagram and the process. What's the next thing I do? The next logical thing I do, if I've drawn my PV diagram, I can visualize the work out, can't I? That's the next logical thing to work on. The work out is the integral of m times integral of p d little v. And there it is. It's that shaded area. It's the area of a rectangle. And so now I see, okay, I think I should work on the work next. And let's see. So I've got the pressure. I need delta V. I need V2 and I need V1. How will I get those? I need V2, need V1. I'll go to the back of the book. I'll bet I can look up, use property tables to get little V2 and little V1. I know the mass. I'll be home free on the work. Perfect. Okay. If you are assigned in your class to draw the TV diagram, if you're assigned to draw a TV diagram, here's what it would look like. Well, here's my vapor dome on the temperature-specific volume diagram. I learned that my process is constant pressure. So that means that I'm going to be following an isobar, a line of constant pressure. And so my TV diagram would look kind of crazy, wouldn't it? But it is the way it would look. I'm going to start at 19 degrees C on temperature. I'm in compressed liquid. I'm going to follow a line of constant pressure all the way up into the superheated zone where my temperature is 120 C. And there I am, and I've labeled my isobar 120.6 kPa. So if I were assigned to draw the TV diagram in my class, boom, I'd put that down. If I weren't assigned to it, I wouldn't draw this. But by golly, I would draw the PV diagram so I can visualize the work. Okay, next step, I need to evaluate the needed properties. And so let's work on state 1, which is a compressed liquid. It is my hope that in your head now, you go back to chapter 3. What do I know about compressed liquids? I remember that the properties, specific volume and internal energy, are functions of temperature only. They're strong functions of temperature only. And so in our training, we learn we're going to go to the temperature table and look up V sub F and 8U sub F in our saturated liquid tables columns to write down V and U at state 1. Well, why am I writing down? So V, you need that for the work. Why am I writing down U as well? I'm looking ahead. I remember heat transfer. I remember first law in my mind. I've got a picture of the first law in my head. I need internal energy. So I'm just going to write down U1 as well. So anyway, there we go. I've gone to my temperature table. I found 19 degrees at state 1, and I'm writing down my V sub 1 and U sub 1, both saturated liquid properties at the temperature. All right, let's move on then to state 2. Giveaway, superheated vapor. I'm going to write down the two properties, pressure 120.6 and temperature 120. Going to go to the superheated tables and darn it, 120.6 kPa is not tabulated in the superheated tables, but 100 kPa is tabulated and 150 kPa is tabulated. I've got to interpolate. So here's the way to do this. So you've got a row 120 degrees C. So you need to write down numbers from your V and U tables. Okay. So for example, you got your number, your V at 120.6 has to be interpolated in between the number 1.188 and 1.793. And your U value has got to be interpolated somewhere in between 2533.3 and 2537.3. So you need to be able to do that linear interpolation. And of course, we're in a hurry here, aren't we? And so I'm going to give you those results. The numerical results are V2 in between those two numbers is 1.544, and U2, little U2, is 2535.65 kilojoules per kilogram. Oh, and of course, units of little V2, cubic meters per kilogram. So linear interpolation needed. If you're uncomfortable with that, watch my video on how to interpolate. Okay, now we've got V1 and we've got V2 by looking up those values in the tables. Now we can numerically evaluate the work. Work is M integral PD little v. There we go. It's not a formula. You can just derive that out of your head by starting with work out as integral PdV. Okay. And so numerically, M, 3 kilograms, P, 120.6 kPa, delta V, whatever that difference is. And so we're going to get a workout of 558.2 kilojoules. We're halfway there. Okay, next, let's see, what do we got? Now we're going to write the first law of thermodynamics to work on the heat transfer. That's the only way I know to get the heat transfer. So we'll write out of our heads. We don't need a formula for this. For a closed system, Qn minus work out is equal to delta U plus delta Ke plus delta Pe. No change in kinetic or potential energy. We'll strike those out. Let's see, delta capital U, that is M times delta little u. And we looked ahead, look, and we determined U2 and we determined U1 in our table lookup work, the mass we have, the work out we just determined. So plug and chug, the heat added is 7926 kilojoules. So there we go. We have fully solved the problem with the help of our PV diagram. And so there it is. There's our summary. The work out, 558.2 kilojoules. The heat added, 7,926 kilojoules. That's an example of a constant pressure process and the way we used our PV diagram to great advantage. Problem 2, example would be a constant temperature process. So I'm going to read this problem and you read along. Refrigerant 134A, well, here's a picture of what an HVAC contractor would bring in if you're running low on refrigerant in your air conditioning system. Refrigerant 134A with a mass of 2 kilograms is contained in a closed system. It undergoes an isothermal quasi-equilibrium process. Now, there's some key words. Isothermal quasi-equilibrium process. The initial state of the refrigerant is defined by T equals 0 degrees C, initial state, and a quality of 5% saturated mixture initially. The pressure of the refrigerant at the end of the process is 100 kPa, tells you the final pressure. Determine the initial and final volume of the refrigerant and depict the process on PV and TV diagrams. So let's see, you're assigned to draw the PV and TV diagrams, and you're asked to find the initial and final volume in cubic meters. Let's see, okay? So let's look for some key words here, okay? And what do we really have to find? What is our assignment here? Refrigerant 134A, that's going to be a phase change substance. Closed system, it says it right there in the problem statement, so we have a closed system. We have an isothermal process. That means it's constant temperature, and the initial temperature was given as 0 degrees C, so we'll just write down T1 equals T2 equals 0 degrees C. And all we are asked to find in this problem is the initial and final volumes, V1 in cubic meters and V2 in cubic meters. That's all we're asked to do. And so let's see, let's plan ahead before the mass is given. So if we can figure out little V1 and we can find little V2, we've got it made, right? And then we've also got to plot our process on PV and TV diagrams. It's an isothermal process. Well, let's start with a sketch. And I wrote down some given information. So here's our sketch. It said closed system. It didn't say anything about piston and cylinder, but it did just say closed system, didn't it? So I'm going to depict this as a piston and cylinder with heat added, work out. Okay. Here's our closed system with a known mass. Okay. T1 equals T2, given in the problem. X1 is 5%, given saturated mixture. It discloses what is P2. And it says, well, wait a minute, look, P2 is given and T2 is known. So looking ahead so we can plot what our process on the PV and TV diagrams, we're going to need to determine the phase of state 2 since we know T2 and P2. That gives us a path forward. All right, so let's use our temperature table to determine the phase of state 2. And then at the same time, we know we've got a saturated mixture at state 1. So let's look up VF1 and VG1 so we can determine the specific volume at state 1. So we're going to do a couple of things here. Okay. So we're given X1. We know we're under the dome. So we'll just immediately in our temperature table go to 0 degrees C and write down V sub F and V sub G. There they are. Just write them down, scrap of paper, or in your solution somewhere. There's VF and VG. I should say on your solution, not scrap of paper. Okay. So we know we got a saturated mixture state 1. So that's sort of check. State 2, P2 is 100 kPa. Now let's go back to think about part 1 of this video. And it says the pressure, the saturation pressure at 0 degrees C is 293 kPa. That's the saturation pressure, 293 kPa. Think about that in your mind, drawing a PV diagram. 292 kPa. Our pressure is 100 kPa. It's less than that pressure. And if you go back and think about that phase study, how do you determine the phase of a substance? You're going to come to the conclusion that since this pressure is lower than the saturation pressure at 0 degrees C, our phase will be superheated vapor. Okay, if you can't do that in your head, go back and look at video number 1. Okay, so let's move ahead. Now that we know we have superheated vapor, we can go to our superheated vapor tables and we have T2 and we have P2. We're just going to shop around. Well, here's P2, 1 bar, okay, 100 kPa. And here's T2, 0 degrees C. So we're just going to write down, all we got to do is write down V2, 0.21587 cubic meters per kilogram. So that's golden. We'll write that down in our solution. Let's draw the process on a pressure volume diagram. It's an isothermal process, PV diagram. Let's draw in an isotherm and label it 0 degrees C. So we're along this isotherm line. We're starting at a low quality. That's why I put my dot sort of over to the left there, okay? And we're going to a pressure of 100 kPa. Well, here's a pressure here of 292.8. We looked that up as the saturation pressure at 0 degrees C. So we've got good y-axis labeling. We're going to end up in the superheated phase, and we're going along a line of constant temperature. Now, okay, great. We were not asked to find the work out, but can you visualize what's the work out? If you were assigned to do that, how would you approach it? Can you visualize what would the work out be by looking at this PV diagram? You'd have to somehow figure out how to numerically evaluate this area under the curve, but we weren't asked to do that. That's just a little extra credit there. What does our process look like on a temperature-specific volume diagram? We've drawn the dome. We've got to draw an isotherm. Wow, isotherm. TV diagram. It's a horizontal line. So all we have to do here is we have to plop down our state 1 near low quality. That's why I put it sort of near the left-hand side of the dome, and going out at constant temperature to superheated vapor, put dot number 2, state number 2, anywhere in the superheated zone, and you got it made. And I've gone ahead and labeled the pressures, but look, if you're under the gun, if this were a test problem, you wouldn't even have to label these pressures and stuff like that to get full credit. Okay, now the numerics of the problem. We're simply assigned determine capital V1, capital V2. We know the mass. Let's see, we've got to figure out what V1 is. Well, we'll just use the definition of quality, and our lookup values that we wrote down to get V1 is 0.004178. So V1 is simply the mass times specific volume, or 2 times that, 0.008357 cubic meters. What's V2? The mass times the V2 that we wrote down. So capital V2 is 0.4317 cubic meters. Okay, not so bad. And on this problem, we were not asked to find the work out. We weren't asked to find the heat added. So we're in good shape. We're done with this problem. Third and last example. Now I'm kind of disclosing constant specific volume process, but let's look at the problem statement so you could figure that out on your own. A two-phase saturated mixture of propane with a mass of 5 kilograms is contained within a rigid vessel, okay, with an initial quality of 65% and a temperature of 28 degrees C. The contents are slowly cooled, so heat is removed. Qn is a negative number. Contents are slowly cooled until the temperature of the propane reaches 16 degrees C, so it's cooling. 28 degrees C starting out, 16 degrees C at the end. Determining the following: the final quality, the work done during the process, and the amount of heat transfer during the process. All right, so let's dissect the words given. And let's see what we got here. Two-phase saturated mixture of propane. Well, that's state 1. So it's, let's see, substance is propane. It's a phase change substance. And also discloses two-phase mixture. So we know we're under the dome at state 1. That's a giveaway. Okay. Rigid vessel. That is a key word, isn't it? It's a closed system. And it's also a key word. Rigid vessel is a key word for something else, isn't it? Constant volume. Okay. The work done, that should pop right in your mind. The work done, if I can look at the area under the curve on a PV diagram, I've got it made. Integral PDV. Heat transfer, going to use the first law. That's that little trick, that little hint. You see the word heat transfer, you're probably using the first law. Let's start with a sketch. Well, pretty simple. Rigid vessel, I've shown heat in, I'm showing work out. You know what we're going to discover there. Labeling mass constant. Another thing I'm observing from my sketch is that since the vessel is rigid and it's a fixed mass, then little v2 equals little v1. Got it. Next logical step, draw the PV diagram with some given information. State one, X1 is 65%. So I know I'm under the dome. Plop down state one, okay? And it gave 28 degrees C. So I'm going to show that isotherm as 28 degrees C. Given in the problem, it's cooling down at constant specific volume. So it's a giveaway, isn't it? This process is a vertical line going downwards. It's cooling down, 28 down to 16. You're going to a lower temperature. You're going along a vertical line since V2 equals V1. There's your process. There's state two. Can you visualize the work out from this PV diagram? What's the integral of PdV? 0. There's no change in volume. dV is 0. So mathematically, the integral is 0. So we're halfway there already. Work out 0. If you're asked to draw this on a TV diagram, well, there we go. Same general idea. There's our vapor dome, and very repetitive, isn't it, in terms of a constant volume process, and we're going from 28 down to 16, so we're going vertically downwards to a lower temperature. So that's really a pretty easy sketch. To get full credit, of course, you'd want to show that you're staying underneath the vapor dome for this entire process. Okay, so let's plan ahead and look up our properties. Since we know we're going to have to use the first law, we know we're going to need little u. We need to find the specific volume, don't we? So we're given the quality. We need to find the specific volume V1. So we're going to have to look up VF and VG and use definition to find V1. Then we know V2 equals V1, right? And if we know V2 equals V1, we can go to our 16 degrees table, and we're going to have to solve for one thing we're asked to solve for is what's X2? What's the quality at state 2? If we know V2 equals V1, then we can write down V sub G and V sub F at our new temperature and use the definition of X, quality, to determine what the quality is. Okay, I'll show you how to do that. But first, we've got to write down 4 properties. So I'm going to write down VF and VG at 28 degrees C. And I'm going to write down UF and UG at 28 degrees C. So it's 4 numbers at 28 degrees. And I'm going to go to the lower temperature, 16, and do the same thing. Write down 4 numbers, specific volume of saturated liquid, saturated vapor, and internal energy, saturated liquid, saturated vapor. Do you see, by planning ahead, you can save time by, rather than just finding your V's first and say, oh, okay, I've got my V's. Oh, now I got to go back into my table and look up U's. Do you see, if you can plan ahead your work, you're going to save yourself time. Man, that pays off in a test situation. You're going to be doing stuff like this in a test situation. Okay, now the numerics of the problem. Okay, we've already got W out equals 0. We looked up the needed properties, and here they are, because we planned ahead. Okay. We determined X. Now we determine X1. We know X1 is 0.65 given. We looked up these numbers, VG and VF, to find that V1 is 0.02966 cubic meters per kilogram. Okay. We know that V2 equals V1. There's V2, so there's a number for V2. We remember the definition of quality, X. Well, it's a ratio. And I've got a typo here. Look at this. This should be V2 minus VF2, not divided by that quantity, divided by the quantity VG2 minus VF2. So sorry about the typo. I think you can figure that out. But we're going to solve for X2, a new number, 0.4652. So the specific volume stayed constant, but the quality changed. The percent of vapor in the mixture changed. Okay, so we started out with a quality of 0.65. We're ending up with a lower quality, 0.4652. Okay, interesting. You say, okay, well, anyway, that's one of the answers, isn't it? The final quality is 0.4652. Next is, let's see, the work we've got. Then it says, what's the heat transfer? We've got to determine the internal energy values. Well, we're just going to use the definition of quality. U1 is X1 UG plus what's left over, 1 minus X1 UF. And repeat exact, that gives us 352.8 kilojoules per kilogram. The same drill for U2 gives us 278.22 kilojoules per kilogram. Internal energy is decreasing. That kind of makes sense, doesn't it? Since the temperature is decreasing. Yeah. Internal energy is decreasing. We'll apply the first law. Q in minus W out. Well, we showed it was 0 equals delta U. That's going to be mass times U2 minus U1. And then kinetic and potential energy changes, we just X those out. No mention of that in the problem. It's a rigid vessel sitting on the ground. Clearly no change in kinetic or potential energy. Numerically, Qn is a negative number. It's negative 372.9. Well, okay, so let's summarize. Here was our PV diagram that saved us lots of time calculating the work. Man, imagine if you tried to apply some formula on your formula sheet for work in a test situation when you could have just visualized with a PV diagram, work out is 0. Imagine that. Imagine trying to go through a calculator, applying some formula when the work out is right in front of your eyes. Wow. Once we got that, we applied the first law of thermodynamics to get Qn as negative 372.9. In other words, heat, I wrote out in my solution to make it clear that I understand about heat transfer in and heat transfer rejected. Heat is rejected from the propane in the amount of 372.9 kilojoules. So I just wrote that out. Okay, we have blazed through 3 examples. So if you got confused, I just encourage you to maybe replay the video where you got confused. If you had a trouble determining maybe how to pin down the phase of a substance, go back and watch video 1. All 3 of our examples were closed systems. We looked at a constant pressure process, and for that constant pressure process, I tried to illustrate how you were able to visualize for the work out using the PV diagram. We then looked at a constant temperature process and observed that, man, it's a horizontal line on a TV diagram, so that's like a giveaway if it's a test problem, right? Okay. Also, it's kind of a tricky process, tricky looking process on the PV diagram, but it does follow an isotherm, one of those dogleg lines, okay? Then the third one was a constant volume process, a rigid tank. We showed that it was a vertical line on both PV and TV diagrams. We really exploited the PV diagram and saw with our eyes that work out was 0. Big time saver in a test situation, right? Okay. And then we're able to numerically evaluate. And so for this particular process, we were it was pretty easy to evaluate the 2 specific volume or the 2 quality values and the 1 specific volume. V2 equaled V1. So we've blazed through 3 example problems, complete with numbers. And so it's my hope that these 3 example problems, complete with numbers, can help you either get up to speed if you feel like you're lagging a little bit in problem solving. And those 3 I selected because so many of your problems so far in the class have been closed systems, and typically they've been one of those 3 categories of problems. So I really hope that that helps. Don't hesitate to come online and ask questions. And stay tuned for video number 3, where we get into some computational details, maybe not quite so important, but can help those of you maybe contemplating graduate school and also those that want to dive down into what's the shape of these isobars and isotherms, that type of thing.